Hey guys, welcome back. Today we're going to be talking about earthquakes, I should say, and Earth's interior. We're going to be talking about the structure of earthquakes and how they move through the Earth, and of course that gives us information about what's inside of the Earth. It's almost like giving the Earth a giant sonogram, the same way that we would look at babies in the womb, for example. So with that said, let's go ahead and dive right in and start learning about earthquakes. Here we can see some damage from an earthquake. This is an earthquake that occurred in Northern California at some point. During an event called the Loma Prieta earthquake in 1989. And here we see an overpass that has actually collapsed down onto this lower section down below. So anyways, we can see right away that this is something that has fallen off of this piling over here. The real question is what is it that brings that about? Is there something in the earthquake motion that does that? Why wasn't it able to sustain this? Well, in order to really understand what causes buildings to fail and things to fall, we have to understand something about earthquake waves or seismic waves right at the very get-go. So it turns out that our analysis of earthquakes has to begin with something called a fault. A fault is an area of weakness that exists in the Earth. And basically, we can define a fault as basically a zone where you have rocks moving next to one another, past one another. Here we actually see some white-colored rocks and some dark-colored rocks. These are both sandstones of different kinds. But notice that these layers here stop right here, and these layers here stop right there. That is not how they were deposited. If we remember our earlier conversations about sedimentary rocks, you don't find layers that just stop and turn into new layers over here. So what is going on in the middle? Right here at this contact, that's a fault. So we actually see a zone where rocks are being moved one zone into the other, right here. And so when this occurs, we can have the potential to create earthquakes, right? The Earth doesn't do it really nicely. It's a dirty job. And when things move, a lot of energy is released, and there's a lot of damage that can be done. So we're going to be looking at these things here. Now, most of these fault movements can be explained by plate tectonics. Okay, plate tectonics is something we've been talking about since the very beginning of the class. So if you don't remember all the details of what moves the Earth's crust around and what might cause it to break, you probably should go back to some of those earlier lectures and review the plate tectonics video. So a fault is an area where things are moving on the crust. Here's a very famous fault. This is the San Andreas Fault, and I'm wondering if you can see it. It should be pretty obvious to you. It's located right here. Okay, this is a creek called Wallace Creek. It's a creek that comes across the fault, and notice that what's happened here is the creek is right here, and now it jumps over to here. Same thing with this other creek right here. It moves over off to the left. So when this happens, as it goes across, we can actually figure out the motion of the fault, how this fault is actually moving. And sure enough, we can recognize pretty rapidly that these arrows represent the movement of motion relative to these two sides of the fault. This side over here, this block of land on this side is moving off to this direction, and this one over here is moving off to that direction. Now, if I was standing on this side and looked across the fault, I would notice this is moving off to the right. And if I was on this side looking over across the fault in this direction, it'd be moving again off to the right. Right? So in terms of what we call relative motion, we would say that this is a right lateral fault, or a right lateral strike slip fault. We'll be explaining what those are in this lecture as well as in a future lecture. So there are three kinds of faults that we have defined so far. There are basically normal faults, which are associated with divergent plate boundaries. Not always. I mean, we get normal faults all over the world, but this is where the main big ones occur. And this is a situation where we get extension, right? So we get a block being pulled this way, a block being pulled that way, and there's a slide plane with an angle right here in the middle. All right. In contrast, we get a reverse or a thrust fault. A thrust fault is one that is at a lower angle, so we'll show this here in a minute. But here's a reverse fault. In this case, they're being pushed together. And as a consequence, it's one side is moving up over the other side. So there's an up-thrown block and a down-thrown block relative to one another. This one might actually be stationary with this coming up over it, or vice versa. You get the idea. It's all relative. In the case of a thrust fault, it's a low-angle fault. So here's the up-thrown block, and it's riding up a low-angle ramp. Here's that ramp right down here. Okay, so this is a thrust. This is just a typical reverse. And of course, we should note that that these thrust faults produce most of Earth's powerful earthquakes. Some of the biggest earthquakes in history, magnitude 9s and greater, are generated on thrust faults. Strike-slip faults are really important too. These are large faults associated with transform plate boundaries. And the most famous example is one I just showed you, the San Andreas Fault. So small strike-slip faults are associated with divergent plate boundaries as well. But anyway, we want to show what these transform boundaries look like. And here we actually see one moving off to the side, this one moving off to the side. These small strike-slip faults are fairly complicated, and I'm not going to spend any more time in this lecture discussing them, but they are worth reading about in the literature. So what is an earthquake? Right? So we know what faults are. Here's, as a matter of fact, here's a fault scarp right here. Here's a fault, and we can see that this is with the arrow going down, this one going up. This is a normal fault. And so what happens over time? Well, an earthquake is simply a vibration of Earth produced by the rapid release of energy, typically along a fault, right? So the energy released radiates in all directions from its source, and we call that source the hypocenter, the focus. This is the hypocenter right down here. This is where the actual breakage of the rock occurs. And we usually show it as a little point, but it's actually a plane. It's almost like ripping paper or slide. You know, if you take your hand and you move your hand, there's not a central point where your hand's locked up where it starts to slide, right? It'll all break along your entire hand. Think of it that way. But we usually find the center point, and we define that as the hypocenter. The epicenter, which is something that most people are familiar with, is actually the point of land right above the epicenter, or I'm sorry, right above the hypocenter. So if I go from the epicenter to the hypocenter, it's just down here. The epicenter tells me the location, but it doesn't tell me the depth. The hypocenter gives me both. The energy is in the form of waves, so we see waves coming out away from there, almost like sound waves. We'll be talking about the different kinds of waves momentarily. And sensitive instruments around the world record the event. So if you're in Paris, or if you're in Siberia, or if you're in Buenos Aires, you're going to be able to detect a large number of earthquakes on these instruments. And these instruments are called seismographs. So how do faults cause earthquakes? So let's talk about the mechanism. So the mechanism itself is called elastic rebound. This is the current theory for how these things occur. And it's basically a three-step process. So a geologist by the name of Reed came up with this idea, and basically that rocks on both sides of an existing fault are deformed by tectonic processes. So here we have rocks here, and here's an old fault trace, right? And what's happening is rocks on this side want to go up, and these rocks want to go down. And right now they're kind of happy, but over time, that rock starts to bend up, or bend over and bend down here. And it's basically storing up a elastic energy, almost like energy inside of a spring. And then over time, it builds up, and then finally it ruptures. So at time 3, so it's time 1, time 2, time 3. At time 3, you'll see that it ruptures. And this is actually a release of energy. This is the storing up of energy. So we go from 0 energy to full energy to back to 0 energy again. It's a cycle. All right, so the earthquake mechanism is where we have slippage at the weakest point, or the focus. So the focus would be somewhere located along this fault down at depth. The vibrations occur as the deformed rock springs back. So it's the springing back from this stage to this stage that brings about that earthquake. Remember, this can occur very fast, in about a minute, or even a few seconds in some cases. Back to its original shape. Earthquakes most often occur along active faults whenever the frictional forces on the fault surfaces are overcome. So if there's friction on the fault, you'll get earthquakes. The San Andreas Fault, for example, has a section in it where there's very little friction. It's very, very small amounts of friction. So there are earthquakes that occur there, but they're very, very small. They're so small that we don't really worry about them. Okay, but when we go down to the area, say in Los Angeles and then up north in San Francisco, there's tremendous friction built up there, and so you get very large earthquakes as a consequence. So those tend to lock up. A couple of other types of earthquakes besides the main shock, the main earthquake, are these smaller types, right? And basically these smaller types are just adjustments in the rocks, and they could come before or after. So one that comes before is called a foreshock. One that comes after is called an aftershock. So adjustments that follow a major earthquake often generate smaller earthquakes called aftershocks. I'll show you some demonstrations of this shortly. But small earthquakes called foreshocks often precede a major earthquake by days, or in some cases as much as several years. And so here's a fire truck that is parked outside of a fire station in California because they've detected a foreshock, or what they believe to be a foreshock, in anticipation of a major earthquake. So the study of earthquake waves is a discipline called seismology, and it dates back about 2,000 years. The Chinese had been doing it at least 2,000 years ago. It's actually quite possible that there's other civilizations that had developed techniques. Unfortunately, that information hasn't come back to us. And you might be asking yourself, well, if it's earthquake waves, why aren't they called earthquakeology or something like this? And the reason why is the word seismos in Greek means earthquake. So this is the Greek word for earthquake, so this is earthquakeology. So we really are saying seismology and earthquake study in the same word, so it does fit. So seismographs are instruments that record seismic waves, and basically it records the movement of Earth in relation to a stationary mass on a rotating drum or magnetic plate. That's how it works now. You know, the ancient Chinese, back at about the time of the Roman Empire, and even maybe before that, had already developed a primitive seismic device that could actually measure the direction that the earthquake waves were moving through the Earth. And basically the way this worked is you had a vase or a big vase here, and these dragons around here were kind of situated above these ornamental frogs, and notice the frogs have their mouths open. What would happen is you would take a ball and you'd put the steel ball in every single one of the mouths of these dragons. And what would happen is as the wave came through, it would move the vase, but the ball that was steel would be in the mouth would be so heavy that it would have inertia, so it wouldn't want to move with the Earth. And so as a consequence, the vase would move, the ball would kind of stay kind of like Wile E. Coyote hanging out in the air in the Wile E. Coyote show, or in the Roadrunner show, if you guys know the reference. If not, you should Google it. But basically, the ball would fall out, and it would fall into the mouth of the frog. And so after the earthquake, they would come out, and they would detect usually that, in this case, there would be, if we had an earthquake going from left to right or from right to left, we would find a ball in the mouth of this frog and a ball in the mouth of this frog. But because there was no motion in the other directions, it would simply rattle back and forth. We would actually see that the dragons, these three dragons on this side, and of course the other three on the opposite side, would still have the balls in their mouths. And so you could actually figure out the direction. And the Chinese were very good at recording this information, at least for a very long time. So we actually have some records that go back quite some time. Unfortunately, political unrest and change that has occurred, especially since World War II and even a little bit before that, has seen many of the monasteries that housed a lot of this data destroyed or damaged, which is unfortunate. So anyways, but you guys get the idea that we can now actually develop a record of earthquakes over very long periods of time. How do we collect this data now? Simple principle, it's not that different than what I just described in the seismograph of the Chinese, right? In this case, instead of using a dragon holding a ball, we have a tall, basically we set up a pendulum. And the pendulum is a heavy mass. So another ball here, in this case suspended by a string from basically a pendulum apparatus. What will happen is the heavy mass resists motion. It has inertia. It wants to stay at rest. This is Newton's first law. Things that are at rest tend to stay at rest. Things in motion tend to stay in motion. So if an earthquake begins to occur, what will happen is the seismograph will start to move, but the ball will try not to. It will resist it. And so as a consequence, if you've got paper sliding underneath here and the Earth is moving, what will happen is that there's a pen at the bottom of it will scratch out basically a scratching of the waves coming through. All right, so that's how the basic seismograph principle works. Now, the techniques that we use now are very similar but different slightly, but you get the idea. And so when an earthquake hits, in this case, the earthquake is hitting right here while the paper's going. There's an earthquake going on right there. Today, we need to kind of recognize that more than one type of seismograph is needed to record both vertical and horizontal ground motion. So today we not only have it going this way, side to side, but we also have them on its side so we can recognize the up and down motion also. And we record both of that data, those data lines. And these records, are obtained and we call them seismograms. We record them and we archive them for long periods of time. Here we can actually see a series of earthquakes on this line, but over here we don't see any seismic activity at all worth noting, or actually it's actually drawing it right through here. Okay, this is a really cool seismograph. We don't use this type of technology so much anymore. Instead, we use computers to do a lot of our work, and so we don't actually use, well, we can, but we don't typically always use a lot of recording paper. It's cumbersome and difficult to keep records of. Computers are much more efficient. So let's talk about the different kinds of waves. First off, There are several kinds of waves that are emanated from a single seismic event, a single earthquake. There are surface waves and there are body waves. The first group we're going to talk about are the body waves. So body waves are waves that can travel through Earth's interior. Surface waves are just only up on the surface. We'll be talking about them afterwards. There are two types of these. There are the P waves, which are primary waves. And these are basically, they're called primary waves because they're fast. They tend to hit you first, primary meaning, first waves. So these are push-pull waves, and they compress and expand in their motion. And basically it does it by changing the volume of the intervening material. And it basically applies pressure. And so we can actually see over here, off to the right here in this graph, a series of pressure waves moving through a medium here represented by the grids. And you can see it's a pulse where we see an area where it's compressed, and right behind it, it's actually decompressed. Let's see that again. So here's the compression, and right back here is the decompression, where it's all spread out. By the way, those of you that study this, the compression, this area back here behind it is called a rarefaction. All right, so these kinds of waves can travel through solids, liquids, and gases. In fact, this is the kind of wave that we see in sound waves. Basically, it's a sound wave that travels through the Earth. And generally, in any solid material, P waves travel about 1.7 times faster than S waves, which is the secondary type of wave. So this is the P wave. It's a pulse that comes through. Let's watch it one more time. And it goes through. Here's a seismogram where we can actually, don't worry about the word minute mark here, but here we actually have a seismogram come through. The first wave to hit will be the P wave. Even though the P wave and S wave are both generated by the same earthquake, they don't arrive at the seismograph, which is some distance away from the earthquake, until different times. So the P wave will hit first, and then you'll hit an S wave, and then some surface waves will come in behind it. The surface waves are the slowest. The second kind of body wave are called secondary waves, S waves. Now remember that P waves had pressure, they were also primary. So you got primary pressure, and they all kind of match to the same thing. It's really convenient. S waves have actually the same kind of advantage. The secondary waves also move in a shear fashion, which also starts with the letter S. Shear means from side to side, right, at right angles to the wave direction. And it travels only through solids. So here we see a demonstration of this side-to-side motion. Here's a wave coming through right now. So this is up here, this is down here. And so this S curve is kind of moving through here. This is a shear, side to side. Again, here we can see it coming through. We'll keep that animation going. And it's a slower velocity than the P waves. But it also usually has a slightly greater amplitude than the P wave. So this is a more destructive wave. This is the kind of wave that moves things from side to side, right? It's kind of hard to engineer a building to deal with side-to-side motion. It's really easy to deal with motion straight up and down because we're already building it to resist gravity. But side-to-side is a lot more complicated, especially if you're building skyscrapers. And so here we see an earthquake. This is in Janus, Oklahoma. This is a 1995 event, and here we see a seismogram where we got the P wave come in first. It settles in, and then here's the S wave right behind it. This volume of shaking right behind it is actually a measure of energy. We'll be talking about that a little bit later. But notice that as we go on through some time, see here we have it, time 1552, and this is 1553. So this would be about 40 seconds in. Notice that a couple of minutes later, so this is 53, 54, 55, right at the 55 mark, we have another one, a P wave and an S wave. You notice the distance between these two is the same as the distance between these two. It implies it's coming from the same place. That would be an aftershock, a small aftershock that's coming in. Now we know that this is not a really large earthquake. Actually in Oklahoma it would be a large earthquake, but most of the world it's not the biggest earthquake. This is a magnitude 4.2. And this would wake people up and hopefully not do a whole lot of damage. But anyway, you get the idea. So we actually have a really cool diagram to show you here. This is a body wave motion. This is P waves and S waves coming out of the exact same source. And we can see that the differences in their velocities can be demonstrated quite rapidly, right? So here we can see, let's see if we can pick out the P wave. Here it comes. This is our P wave right here, right at the front. Now they start at the same time, and then the S wave comes through. So let's watch that P wave, S wave again. Here's the P wave. P wave and the S wave both start at the same time. This is separated out. Now here's the S wave still coming through here. So this is them moving together from a single source. One last time here. And you can see that the P wave is a lot faster. Cool. All right, so there are two kinds of surface waves as well, and they kind of are similar to what we're talking about in the P wave and S waves. These surface waves have two types. They're the Love waves and the Rayleigh waves. And these travel along the outer part of the Earth, basically the interface between the land and the air. And they're kind of analogous to the kinds of waves that you find in the ocean, for example, where you see an interface between the ocean and the air as well. They travel along the outer part of the Earth. There's a complex motion involved. There's a lot of very complicated mathematics. We won't be describing any of this stuff other than or discussing any of the mathematics, but we'll be kind of trying to describe their motion just really briefly in this slide. These cause the greatest amount of destruction by far. So if you're in an area where you get large surface waves, you're going to experience some damage. Waves exhibit greatest amplitude and slowest velocity. They're very slow. They also actually dissipate relatively fast as well, which is good. So as long as you're relatively far from the epicenter, there's a good chance that you might be able to escape the surface waves. The P waves and S waves you'll still have to deal with, but the surface waves are by far the most dangerous. These waves have the greatest periods, which is a time interval between crusts, and the most common experience that people describe is something called ground roll, where the ground literally feels like it's rolling. And that's due to the Rayleigh waves as they're rolling through here. You actually feel like you're moving back and forth, in this case, motion like this, even though the wave is actually moving in this direction here. So let's look at the difference between body waves and surface waves in terms of how they behave on Earth. First off, here's a hypocenter, somewhere near the North Pole. This hypocenter erupts or ruptures. There's an earthquake generated, and there's surface waves that come out of the situation. There's P waves and S waves that come out of the situation. We'll describe the paths here in a moment. But notice that at these 3 points we have seismographs. And so let's start interpreting what we see here. We see seismograph 1 has got P waves, S waves, and surface waves, and it's the closest to it. So we can look at this difference here. Now we know that seismograph 2, which is located further away, should have things coming in at greater distances. And sure enough, the difference between P wave and S wave here is greater than it is right here at the one close. And then the surface waves come in even later. At the same time, seismograph 3 registers P waves, but the S waves, which are slower, are not quite there yet. And yet again, the S waves, which are the surface waves, which are the slowest yet, are still way back here, not far past seismograph 2. So you kind of get the idea of what we would expect to see between these three seismographs. You might be asking yourself, why do they draw these arrows as curves, right? And the reason why we draw these arrows as curves, and we haven't really talked about this a whole lot, about in terms of wave behavior, but in physics we understand that when waves enter areas of higher density, they tend to refract, and that's the reason why you get rainbows and so on and so forth forming on Earth and in our atmosphere, is because different densities, you got water droplets in the air, and it basically refracts light. P waves and S waves are waves, just like lighter waves. And so they have a similar behavior. In this case, they go from high density or low density into higher density material, because as you go down towards the core in the Earth, things get under higher pressure. Higher pressure means things are packed more closely together, which means a higher density. So you wind up getting these refraction curves. All right. Now we're going to come back to this drawing later on in the lecture to describe, use this to show how we know what we know about the Earth. It's pretty neat stuff, actually. So let's get some terms out of the way. First off, we've described this. Let's just kind of hit it again. The focus or the hypocenter is the place within Earth where the earthquake waves originate. The epicenter is the location on the surface directly above the focus. So it's actually pretty easy, it turns out, to find the epicenter. The hypocenter is a little more difficult. It's kind of difficult. You need some really good data to be able to find the hypocenter. But the epicenter can be found pretty quick. And the epicenter is located using the difference in velocities of P and S waves. So here we see we've gone through and over time, and we realize that the P waves kind of travel at a consistent velocity. And so we know about how long it takes for it to get certain distances away from earthquakes. The same thing with S waves. S waves take longer, and so their curve is way up here. And so we can look at the difference in the arrival time to figure out the distance. So if we were looking at a seismograph, let's say, well, let's go back to this one here. We were looking at seismograph. This one here, seismograph 2 says 1 minute for each one of these bars. So P wave comes in here, so we'll call it 0. Now let's count to the S wave. 1, 2, 3, 4. That's 4 minutes until we get to the S wave. Let's come back to this curve. What we want to do is find out where the difference between the S wave and the P wave is 4 minutes. And so it looks like it might be 1, 2, 3, 4, probably about right here would be about 4. And then we'd read it all the way down to the bottom, and we notice that that gap gives us a 2,800 kilometer distance. Cool. So we can actually figure out how far away the earthquake occurred by looking at the difference in the arrival times between the P wave and the S wave. Really neat. Each station determines the time interval between the arrival of the first P wave and the S wave, and the time travel graph is used to determine each station's distance to the hypocenter, or I'm sorry, to the epicenter. Okay. So we can actually use our seismograph and figure out how far away the event occurred. But that doesn't really tell us where the epicenter is. It only gives us a circle of possible distances, a range, if you will, of distances on a circle. Or a radius, actually, I should say. So what we can do, though, is we can take several of these seismograms and compare them. And so if we take this one here, and we know that the range is going to be out here somewhere, and we take this one here, say at position A and C, and compare them, we'll notice that they overlap at 2 points. The cool thing about this is that the earthquake has to have occurred at one of those 2 points. If we use the benefit of a third seismograph at position B, check it out. We notice that position B goes right through here, and where A, B, and C all come together, that's the location of the epicenter of the earthquake. They refer to this as triangulation. And so this is actually how GPS tends to work. This is how a lot of really cool technology works. Is you have 3 cell phone towers, you can be located. If you have 3 satellites in space, you can be located if you have the right GPS information. So here we'd see an example of an epicenter that occurred in central China. This would be Siberia up here, Lake Baikal, Mongolia right here, and then so this would actually not necessarily be central, but north-central China. A lot of earthquakes occur here. So we have a seismograph here in Darwin, another one here in India, and another one up here in France. We go ahead and we can figure out the differences between the P wave and the S wave arrival times, and we can get the distance. We put our circle on our globe at all 3 of these. And where they all overlap, notice this right here. They look like they might want to overlap out here, but they don't overlap perfectly. Here they overlap perfectly. All right? And that's basically how seismology, or locating earthquakes, is done. We can use this for all kinds of different applications, but the biggest thing is that if a major earthquake happens, usually the seismographs know about it before the emergency personnel know about it. And so this is one way that we can figure out where to send emergency personnel to help people in trouble, especially if they're in third world countries such as Pakistan, which is located over in this area. Afghanistan is also up in here. So if there was a major event that occurred here, we would know to go there and to be able to help the people that were in need. It's also useful for figuring out if, by the way, seismic waves are emanated from nuclear blasts as well. So if this was a epicenter that was actually epicentered in the nuclear facilities of North Korea or in some other country, we would know pretty rapidly that a nuclear test had in fact been conducted. So how do we determine the size of earthquakes? Well, there's a couple different ways we can do it. Some ways are better than others. The first way that we developed was, it was developed in California. California was kind of the place where we were getting consistent earthquakes. There was a consistent building code across the state, and we kind of knew what to expect. So we developed something called the Mercalli scale, and we can go through and map out the different intensities. So this is something called the Mercalli intensity scale. The drawback to the scale is that the destruction might not be a true measure of the earthquake's actual severity. Some buildings survive better than other ones, right? So that doesn't really tell us that much about the strength of the earthquake, but it was really the best that we had for a very long time. And so you notice pretty rapidly, you know, maybe an intensity 3 is felt noticeably indoors, especially on upper floors of buildings. But 1 and 2 are basically, most people are able to sleep through a lot of these things. Let's see here, a magnitude 8 would be considerable damage in ordinary structures, chimneys, and monuments fall. 9 is very large damage, considerable damage in all structures, ground cracks, underground pipes break, and you'll also go all the way up to 12. this would be an interesting way to look at things. And in fact, we did a seismic intensity map, and the United States Geological Survey still produces these maps for events that occur in the United States. This is the seismic intensity map for the Loma Prieta earthquake of 1989, also known as the World Series earthquake. So the Loma Prieta earthquake, here we see the earthquake actually was centered right here in Santa Cruz. But we find damage all the way up here in San Francisco because a lot of the older buildings in San Francisco weren't built up to the same codes as some of the other areas. And not to mention the fact it was built on inappropriate type of ground fill. And we'll be talking about liquefaction and things like that here momentarily. But notice that the ring of intensity that came out, it affected areas all the way as far away as Reno, Nevada, and Bishop, California, which is along the eastern border of California with Nevada. This is a very large earthquake. There's a more objective way to go about measuring earthquakes, however. The best way was developed by a guy named Charles Richter in 1935. And he was kind of frustrated over the fact that you can have an earthquake that would occur, say, in a remote part of China where nobody lived. And it could be a very large earthquake. It could be a magnitude 8 earthquake, which would be a huge earthquake. We'll describe what magnitude here means in a moment. But a very large earthquake. And if you had a very large earthquake and nobody was there to feel it, how could you get any objective data on that? That was frustrating. And they could see it on the seismographs that it had happened, but they couldn't necessarily figure out the details of that event. So Charles Richter said, we got to fix this. First off, it's based on the amplitude of the largest seismic wave that's recorded. So here we see a seismogram coming through, the P wave comes in, the S wave, and notice that here's the largest amplitude, and you can measure that amplitude. It accounts for the decrease in wave amplitude with increased distance. How does it do that? Because it correlates whatever you see here in your S&P distance. So you know the difference between these two, right? You got the time, you can fit, in this case, 24 seconds. You can use that to figure out its distance. You know the amplitude, you put it over here, and then you basically draw a straight line through the magnitude scale here. And that basically estimates the amount of energy released at the source of the earthquake. And we call that amount of energy, or that estimation, a magnitude. So the Richter scale basically works like this. For a long time, the largest that we had ever recorded in a seismograph was a magnitude 8.9. That doesn't mean that there weren't bigger earthquakes in magnitude 8.9s occurring. In fact, several have. But that was the largest that we were able to detect at that time, for a long time, actually. We also note that magnitudes less than 2.0 are not felt by humans. We don't feel them. So anything below 2, we don't feel. And everything above 2, we definitely feel. Each unit of the Richter magnitude increases to, or corresponds to a 10-fold increase in wave amplitude and a 32-fold increase in energy. This is huge. So to go from a magnitude 2 to a magnitude 3, you are a 10 times larger earthquake. To go from a 2 to a 4, it's 10 times 10, because you multiply it by 10 each time. So it's 100 times larger an earthquake. So here's a nice comparable diagram for earthquakes. And so here we see magnitude scales. Moment magnitude measures the total energy released from an earthquake. There's different ways we can do this. We can actually make estimations from what we could assume that a fault can do. That's what this text here is basically saying. And it can also be calculated by modeling data from seismographs. So anyways, how many earthquakes do we get per year of certain magnitudes? Well, the number of magnitude 0 to 1 or 0 to 2 is unknown. They're so small that we don't even feel them. And the amount of energy released is quite small. It's about 56 kilograms of explosives. 56 kilograms for you guys that are metrically challenged. It's about 120 pounds, I think, is the estimate of explosives. So it's a large amount of explosive, but if it's not right underneath your house, you're not going to feel it. From a magnitude 2 to a 3, there's about 1.3 million earthquakes per year that are felt by human beings. Okay, and the energy release in this is starting to get relatively large. Let's go ahead and jump right up to the largest one, magnitude 9s. There's less than 1 per year. But the amount of energy that is released in this case, instead of being 56 kilograms, it's 56 trillion kilograms. So what is it that determines the amount of destruction that will be experienced in a given vicinity? First off, how close, right? how close you are, the proximity to the epicenter, the magnitude, of course, the amount of energy is released. We've been talking about both of these things. But it also depends on the structures themselves. You know, the earthquake intensity, right? Some buildings can survive better than others. The duration of the vibrations. So some earthquakes only last a few seconds, some last a couple minutes. The ground can move in some cases for several minutes, 4 or 5 minutes. The nature of the ground beneath the structures. Hey, granite, quite frankly, if you have a house built on granite, you're safer than if you're built on wet sand. And of course, the nature of building materials and construction practices of the region. You're much more likely to survive an earthquake in a modern building constructed to Western nations' standards than if you were to live in a more primitive style, you know, maybe something built in Scotland, made out of shingle walls or whatever, that doesn't have any cross bracing, is more likely to kill you. So you don't want to live in a Scottish hut that has shingles that are holding everything up, because you're likely to get buried by the event. All right, so here we see some other ways that destruction can occur. First off, whenever earthquake waves go into soft sediment, the soft sediments tend to amplify seismic waves more than the solid bedrock. Remember I was saying soft sand? And one of the unintended consequences of this, one of the things that we should always be wary of, is that when you build on soft sand, look, the sand can actually start to act like a liquid during an earthquake. Things start to move around and shift around. And so these are buildings that have actually just fallen over because the ground started acting like a liquid during an earthquake. This is the Guatemalan earthquake back in the 1960s. And you can actually generate things called sand volcanoes. This is a very tiny one here. This is a sand blow, so it's a tiny one. But here the liquefied sand actually starts to flow up to the top, and it actually will spurt out during the event of an earthquake. Can these things be predicted? We're working on it, right? We don't really have good answers for a lot of the questions that we have, but we're starting to get a better understanding of what causes earthquakes to occur in the first place. And then we'll be able to try to get in front of a lot of these events. So the goal is to provide a warning of the location magnitude of a large earthquake within a narrow time frame. You know, if we know that's going to happen in the next 10 minutes, we can warn everybody. If it's in the next day, we can warn everybody. Research is concentrated on monitoring possible precursors of major earthquakes. So we can look at changes in ground elevation. You know, the ground, as stress is building up, starts to shift and move around. We can measure strain on the rocks, right? We can actually put a meter down in the rocks that measures how much stress is going on down there. We can measure changes in groundwater level. As you increase the stress in the rocks, the water actually gets squeezed up or squeezed out. And we can see that pretty rapid fluctuation. And of course, we can look at the frequency of foreshocks. And if we see a lot of these things all happening at the same time, we have actually in the past made a prediction that an earthquake would happen, and sometimes it does happen. But there have also been times where all these things happen and nothing happened. So we have to be very careful about making these assessments. Of course, you go and make a prediction that an earthquake's going to happen in an area and it doesn't happen. What have you just done to the economy of that area? Not only have you destroyed real estate prices, but you've also destroyed your own reputation. So you have to be very careful. Currently, no reliable method exists for making short-range earthquake predictions. That's the bad news. Okay? There is a little bit of good news. First off, we can make long-range forecasts. We can look at earthquake records and we can figure out about how often they occur on time scales from 30 to 100 years. The San Andreas Fault, for example, is expected to rupture a little over every 100 years or so. It hasn't done it in a while, so the risk of the San Andreas Fault moving and doing damage to the Los Angeles basin in the near future is actually quite high, and it's growing with each year because that stress is building up on that fault. We can use a couple of techniques other than just simply looking at old records. We can actually look at the earth itself. We can use historical records, like I was talking about the monks and the monasteries in China, to look at those old Chinese records. But we can also do something called Paleoseismology. And this information is useful for developing a uniform building code in an area, and it also assists in land use planning. So Paleoseismology is a cool study. This is where you actually get to go out and dig up faults and learn about them. I'll show you an image of this here momentarily. Another way that we can do it is we can look at where earthquakes have occurred in the past. This would be an example called a seismic gap. Here we see a megathrust fault, which is we'll be talking about this in a couple of lectures. A megathrust fault is a subduction zone. And so here we see a subduction zone that in 2004 generated a magnitude 9.2. This is a very large event. This is the one that killed well over 100,000 people in the Indian Ocean tsunami. But there was also a precursor, a 2000 event that it was a magnitude 7.9 here. 2007 was an 8.4. 2005 was an 8.6. These are all very large earthquakes. All of these are very large earthquakes. But notice right here outside of Padang on the island of Sumatra, which is part of Indonesia, there's a seismic gap. No earthquake has occurred here. Might not be the best place to invest in real estate. Okay. As a matter of fact, there's another one here, magnitude 7.7 in 2010 that I just actually missed. So there are a lot of earthquakes that happen here, but there hasn't been one here. And the question is yet. It's just a matter of time. And the real question is how big and when. Here's Paleoseismology. We come to this again. Here's the Wasatch Fault, and we see a colluvial wedge we can go through. We can look for fossils in here and figure out how old this colluvial wedge is. It's a colluvium is basically the trash that's on top of the fault here that washes over and builds up along it. And so we can go through and we can study the relationship between these two, and we can actually get a pretty good idea of how often this fault actually moves. It's a really cool study. We're not going to be able to get into it beyond just this slide in the class, but know that people get PhDs in this, and it's really neat to actually go and be able to put your hand right on the fault and say, here's the crack in the earth that creates the San Andreas Fault. On one side of my finger is one plate boundary, and on the other side is another plate boundary. So if this was the San Andreas Fault anyway, you could do that. It's a fun thing to study. So now we actually have the tools to be able to look at the Earth's interior. Really neat stuff. We've been kind of giving you the outlay of the Earth's interior, the crust, the upper mantle, lower mantle, outer core, inner core, and we've got all this stuff and we've been talking about it, but we haven't really described how we came about that. And the way that we've done it is through P waves and S waves. So let's do a little review of these things. Remember that there's two kinds of body waves that actually penetrate the Earth. There's the P wave and the S wave. And the P wave is faster than the S wave. This is the same information we presented earlier. And here we see a seismogram of a P wave, and then here's an S wave coming through here with some time gap of, I don't know if these are seconds or minutes, but you get the idea. There's 50 units of time that have passed. And back to this here. Again, surface waves are only on the surface. The P and the S waves have different arrival times. And notice the curvature, right? We talked about the density differences bringing about the refraction of these waves in the Earth. So we actually get density data, very good density data about the mantle of the Earth, as well as the core. But we're going to come to the core. Core is a special circumstance. These are called seeing seismic waves. These are interactions between seismic waves and Earth's layers. Earth's layers all the way down to the inner core. Seismic waves reflect and refract as they pass through the different layers of Earth, and refraction occurs due to the increase in density. We've talked about this. Studying seismic wave velocities gives seismologists a layer-by-layer understanding of the Earth's composition. It's not a complete understanding, but it's something, right? Because we can't actually go into the mantle to actually get samples. It's very difficult to get samples from the mantle. Sometimes volcanoes will generously hand us a sample, but it's not too often. So we have been able to map out the distribution of seismic waves after an earthquake or during the event of an earthquake. And so if we imagine an earthquake epicenter up here, a generic earthquake that occurs at the North Pole, of course we all know that an earthquake likely would not occur at the North Pole very often because there's no plate boundary up there. But with that said, let's imagine there's one here. And what we've determined is that we can put seismographs all around the Earth, and we can see what happens when these epicenter, or when the what happens when an earthquake radiates away from the epicenter. And we notice that there's P waves and S waves that distribute all throughout this outer part up to this point at 105 degrees. Same thing on the other side. We get P waves and S waves. But notice that down here, we don't get any S waves. We only get the P waves coming through. P waves are in black, S waves are in red. These are only P waves. And the reason why that happens is because they can only travel through different kinds of medium. P waves can go through liquids, gases, and solids. S waves can only go through solids. So that means that it's hitting something on the way that it can't travel through, and that's almost certainly a liquid, and we now believe that to be the outer core of the Earth. And so the outer core was actually discovered relatively early. Some other earthquake data came in and allowed us to look at the refraction zones in here, and we actually later on detected that there was an inner core as well. But by looking at these refractions, and we know what's going on, we know there's a consistent angle of 35 degrees here, 35 degrees here. We can use some not difficult mathematics, but mathematics to be able to solve the diameter of the inner core and the outer core and the depth of the mantle. So that's how we got the data. And so here's the result. We see the layered structure of Earth. We got a crust up here. We got a mantle, an outer core. And we know that the lower mantle, for example, is hot but strong because of high pressure. So we know that it's a rocky layer. We know that the asthenosphere is this weak rocky layer that's right below. And this is the zone of the plates are this area up here. This is the mantle kind of down, actually all throughout here. This is the lithosphere, I should say. And the lithosphere is what is actually moving across the Earth's surface in plate tectonics. Okay, I think that we kind of covered this little slide really quick. So we did learn that there were two kinds of crust using this technique. We learned that there's the continental crust, which is heterogeneous in structure and composition. Right? We usually assume it's granite, but it's actually made out of all kinds of different stuff. And it averages about 40 kilometers thick, but there are places it's a lot thicker and a lot thinner. For example, in the Himalayan mountain range between India and Asia, 70 kilometers is how thick it is. That's a very thick crust. But the thinnest area is about 20 kilometers in the basin and range. If you think of basin range, think of eastern Utah and eastern Nevada and western Utah. The average density of the crust on the oceanic crust is the continental crust is 2.7 grams per centimeter cubed. That's 2.7 times denser than water. That's kind of the better way to think of it. The oceanic crust, however, is different. If we've determined that it forms at mid-ocean ridges, we know that it averages about 7 kilometers thick. It's really thin compared to the continents. Really thin. 7 kilometers is not that thick and is composed of basalt and gabbro. And the average density is denser. It's about 10% denser than that of the continental crust, which is why the oceanic crust sits lower on the Earth's surface. All right, and hence is covered by water. Right, if water is going to flow, it's going to go to the lowest part of the Earth because of the pull of gravity. Well, that's going to be over the oceanic crust. We also learned a lot about the Earth's mantle. First off, the Earth's mantle is 82% of Earth's volume. That's a lot. And based on observations of seismic waves, the mantle is a solid rocky layer. It's not liquid. It's not on fire. You know, there's always depicted that way in a lot of the documentaries. But real science would dictate that the mantle is in fact a rocky layer that goes all the way down to the core. The Earth's upper mantle extends from the crust to 660 kilometers deep. So there's actually two separate mantle layers. One from the crust all the way down to 660 kilometers, so there's a kind of a upper crust, or I'm sorry, upper mantle, and then there's a lower mantle, and that upper mantle is composed of peridotite, which is basically an all-olivine rock. Its lithospheric mantle is the uppermost part of the mantle and extends down to 200 kilometers, so we've actually been able to learn a lot about this stuff in the asthenosphere. If you really want to understand this stuff, go back to this slide here, pause it, and take a quick look. This is basically a description of what we're seeing down here to the lower right. The lower mantle extends from the upper mantle to the liquid core, and this is Earth's largest layer, and it's about 56% of the Earth's volume, and we know probably the least of anything about that layer. So we have some ideas of what things might be made out of. First off, we know that there's the Earth's core. The Earth's, the outer core is liquid because the S waves can't get through it. And the outer core seems to have a density of 9.9 grams per centimeter cubed. We can figure that out by the velocity of the P waves going through it, so that we know the density. It's composed mostly of iron with some nickel and with some lighter elements possibly, and it's probably oxygen. Oxygen is kind of common throughout the entire Earth all the way down to the core. The inner core is a solid, dense sphere, and it has a density of 13 grams per centimeter cubed. To give you an example or an idea, gold is just under 20 grams per centimeter cubed, so it's still pretty dense. It's a pretty dense material down there, but it's not quite as dense as, say, gold. But it's about iron. Think of an iron ball in your hand and how dense that is. And basically, this data matches observations from meteorites, right? So when we look at the densities of these things, it turns out that this density matches that of a meteorite. And so here's an iron-nickel meteorite, and we believe that the study of meteorites is like studying the old remnants of old cores of old planetesimals, or from the origins of the solar system, and maybe even material from which the solar system was later derived. really neat stuff. Here's another stony meteorite. This would be something similar to what we'd find along the core mantle boundary. Here we find iron all throughout here, and then stuck inside this iron is a mineral called olivine. So this is a type of a meteorite called a paleosite. Here we see again another paleosite with the olivine. The light shines right through. It's a beautiful rock, actually. These are quite expensive to purchase, but you can purchase them on eBay. Rock collectors love them. And then here's a stony meteorite that seems to have a composition similar to what we would expect for the lower mantle. Really, really beautiful stuff. And of course, we've seen this picture on the previous slide. So anyways, you kind of got the idea that earthquakes generate more than just damage and destruction, but there's actually useful scientific data that we can gather from it about our Earth. Now, if we wanted to get even more precise and even better data, we would have to use nuclear explosions. Fortunately, we're sensible enough to know that going and polluting the surface of the Earth with nuclear explosions to learn about its interior is not worth the price that we're paying. So we haven't gone about doing that. That doesn't mean that people don't fantasize about doing that. But you can get better measurements with that kind of data. But fortunately, we haven't made that step, at least not too frequently. Anyways, with that said, if you have any questions, I hope you really, like this stuff. I know some of it's kind of difficult to maybe understand. You might need to watch this video one more time. But if you have any questions, send me an email or meet me on the discussion boards. Until next time, have a good one.